functions. So, one period. I'm only going to graph one period on the parent function graph. Do we all have a clear understanding that these graphs continue to cycle forever through the values? So if I draw one period, you don't think that is the sine graph. You understand what you did with your arm. Just keep going. Okay. So sine graph starts when you plug in 0. What? At the maximum, at 0, at the minimum? 0. Okay. Then goes to the maximum, then 0, then the minimum, and then back to 0. This is our parent sine function, okay? This is our parent sine function with a period of what? 2 pi. And an amplitude of 1. Knowing those things, yeah, I just changed the pattern. Okay. Knowing those things, yeah, Renee? No, you guys, just take notes on a piece of paper, you know, the way you used to. There will be a note guide online tonight, but you weren't supposed to print it out because I didn't finish it till like last night at 10 o'clock. Okay. Just pretend like that didn't happen. All right? We're just taking notes. All right. So, here's our parent function. Knowing that the period is 2 pi tells me that to cycle through these values takes a distance of 2 pi along the x-axis. If this distance is 2 pi, what is this? You either have it memorized or you can now figure it out. Pi over 2. How many of you guys had it memorized? Anybody figure it out? Dana, how could we figure it out? Okay. Okay, yeah. So we can take 2 pi and we can take a fourth of it, right? If I told you guys the fourth mark on the graph was 20, you guys would tell me the graph was numbered by 5 because 5, 10, 15, 20, right? Because you'd take 20 and divide it by 4. If I tell you that the fourth mark on the graph is 2 pi, then you can just divide that by 4 and tell me that this is pi over 2. Apparently I didn't put the good battery in because... So this is numbered by pi over 2's and follows this pattern. Okay, sine function. Not doing cosecant yet. We'll come back to that another time. Are we good with the way the sine function works? This was in your investigation guide also. Is this all right? Yes? Okay. Our focus today is going to be sine and cosine. Okay? So cosine. What's the period for the cosine function? 2 pi. Okay? I'm asking you guys strictly out of memory. These are things we're going to have to start knowing. Okay? And the amplitude? 1. Ooh, let me go back to my sine graph real quick because I forgot something. These would be 1s. That is important because if it wasn't scaled, I wouldn't know if it was stretched or compressed vertically. Okay? All right, so cosine, again, I'm going to just graph one period of the function. If I start at 0, where does the cosine function start its pattern of points? At 1. Good job, Matt. Okay. Then it hits 0, then down to -1, then back to 0, and then up here. I'm demonstrating this because this is how I remember them. I do have them memorized in a sense that I have this remembered every time. Okay, that the cosine, I start with this pattern of the 5 points, and the sine, I started here and went through the 5 points. Okay. Again, since I know the period is 2 pi, that means when it completes this cycle, that must be 2 pi. Okay? And that 2 pi divided by 4 would give me this first mark here, which means this first mark here must be pi over 2. That's important for me to know because that scales my entire graph. I want every mark on the graph to represent a pi over 2. So pi over 2, 2 pi over 2, which would be pi, 3 pi over 2, 4 pi over 2, and then if I had to keep going at 5 pi over 2, 6 pi over 2, 7 pi over 2, right? Or I can go in the negative direction. I can get all that stuff down. So our focus is going to be on using these two parent graphs today to do some transformation. So are we comfortable with the parent functions based on the investigation results that we saw yesterday? Right? When you do get your note guide, I tried to make this nice little front sheet where all your parent graphs would be. So sine, cosine, tangent, and next to them, cosecant, secant, cotangent. Too bad you don't have it. Okay. All right, really quick in your groups. You don't have to write this down if you don't want to. What I do need you to know them. So I just want literally you guys like 1 to 2 minutes, and I want you guys to make sure that everybody knows in your group how A affects the graph, how B affects the graph, how H affects the graph, and how K affects the graph. So right now, talk with everyone in your group and make sure that they understand from the past or from the investigation what those values do to the transformations. And here we go. Okay, so we're going to graph this. Okay, -2 sine of 2x minus pi plus 1. Yes. Okay, are we ready? Yeah, you guys are enthusiastic today. Yes. Whatever. I'll just be enthusiastic enough for all of us. Okay. So, first thing I'm going to do, this is a sine graph, just like if it was x squared or an absolute value or a cubic. The first thing I would want to know is what does the parent function look like? So that's why we filled those in at the beginning, because I want to remember that the sine function goes here, 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 here. It's like connecting the dots as I'm doing it. Okay. That's my sine function, normally with an amplitude of 1 or -1 and with a period of 2 pi. Is this okay with everybody? I just graphed the parent function. That's it, to start with. I'm going to do a million different graphs. I'm going to do one for each transformation. If you don't like it that way, you don't have to do it that way. Okay? I'm just doing that for the first one, so we get it. All right. So, like it says in step 1, I guess I did step 2 before I did step 1. You do want to make sure that you've written the formula like this. With this 2x minus pi right here, we're not technically seeing the stretch and compression separate from the horizontal shift. We're seeing them combined together. So we do want to separate that. So when we separate that, our equation is going to look like y equals -2 sine. In the sine function, I'm going to factor out a 2. Okay. So what's going to be left in the parentheses right here? Good. X minus pi over 2. Okay. All right. So somebody tell me some of the transformations that are happening here. Alex. Good. Negative tells me vertical reflection. Claire. Good. This over here tells me at the end I'm going to shift up 1. What else? Alex and Claire already gave me some transformations. We all got to be able to recognize them. Julia. Okay, good. We're going to move right pi over 2. Dana? Good. So this 2 is going to change the period. And the way we're going to do that is we're not literally going to compress or stretch our graph. We're just going to change the scale right away so that we've changed it to adjust for our period like we saw on the side of the board. Matt? Good. And this 2 is going to multiply the amplitude by 2. Okay, so from wherever that kind of middle transverse axis is, we don't expect 1 above and 1 below for our maximums and minimums. We now expect them to stretch away from that and be 2 above and 2 below. All right, so the first thing I'm going to do is I'm going to take my sine of x function, and I'm going to make it the sine of 2x. Notice that I'm addressing the period first. We're going to address the period first to change our scale on our graph, and then we're going to be good. So remember what we talked about period over there. I could literally mark it how it normally is and then condense it or stretch it. But if they're using 3s or odd numbers that don't match well with the marks I already have, that's going to be really difficult. So I'm actually just going to keep the shape of my current graph. Like my sine function goes through these points. This is still 1. This is still -1. It still goes through here like this. But what I'm going to do is just rescale my graph so that I show the change in period. Instead of the period being 2 pi, what should the period now be with this 2 right here? So think about your horizontal stretches and compressions. You would take the normal 2 pi, and is this a horizontal stretch or a horizontal compression? Compression. It's really like we're multiplying by 1/2. 2 pi times 1/2 is pi. For this function, my period should now be pi instead of 2 pi. So to adjust for that, all I'm going to do is call this mark pi, okay, which means every mark on my scale for my graph should be what? What should I have that axis scaled by? If you can tell me this, yeah, then we have the scale. Basically, if pi is the 4th mark, remember that you can take that, times it by 1/4, and you can get the first mark that you want on your graph, pi over 4. Once you have that, everything would be adding another fourth to that as you move to the right. So this is 1 pi over 4, meaning the next one would be 2 pi over 4, which reduces to be pi over 2. And then this would be 3 pi over 4. And the next one would be 4 pi over 4, which reduces to pi, 5 pi over 4, 6 pi over 4, 7 pi over 4. Okay, so see how that numbering system will kind of help us a little bit once we get used to just identifying which is which. Now, I've only graphed one period of the graph because I don't want to have to stretch and do a million things to like a bunch of pieces. I'm going to do it to one cycle, get that cycle where it goes, and then extend it in both directions. Okay? All right, are we okay with this one change? So here we've adjusted the period of the graph. Okay? Can I change? Is there any objection to me changing the slide? So the next, you guys have that graph on your paper. I don't have it on my slide, so it makes it a little harder for me. Okay. But now what we're going to do is we're going to change it to this graph that has the period transformation in it, but also the shift. Okay, so you guys have right now this graph that looks like this. You guys should be looking at it. Do you see it, the one we just did? And the way we took care of our horizontal compression is that we scaled our graph. Is that good with everybody? All right, so somebody explain to me what the next transformation is that I'm putting in here. You guys already identified it in the original equation, but I'm choosing to do this one next because it's horizontal. Right? Okay, good. A horizontal translation. Am I moving to the right or to the left? The right. And how much? Pi over 2. Look at the scale of your graph. Pi over 2 means how many marks are you moving? 2. Pi over 2 is here. So pi over 2 is a measure of 2 marks. So I am moving to the right, pi over 2, which to me means the right 2 spaces on my graph. Okay? So that means this part right here that I was calling my starting point is now going to be here. This one is now going to be here. This one is now going to be here. This one is now going to be here. And this one is now going to be here. And if I want to make myself more comfortable with the scale, I can continue those. So this was 3 pi over 4, 4 pi over 4, 5 pi over 4, and 6 pi over 4, which is like 3 pi over 2. Is everybody okay with our horizontal translation? So I would always take care of stretching and compressing first horizontally because you'll just change the scale on your graph, but it'll still look like the parent function. Done. Okay? Then I would do any reflecting. There wasn't any horizontal reflecting in this problem, so we didn't have to kind of flip it over to the left side of the graph. Then I would do my translating, and then I'd move on to my vertical stuff. Okay? So I did my translating. We're done with everything in here, which means we're done with our horizontal stuff. And we're going to move on to our vertical stuff. All right. So the next thing we're going to do is we're going to do these two transformations together. So let me recap what you guys have right now on your paper. You basically have this cycle of your graph now starting at pi over 2. But other than that, it still kind of looks like the parent function. And that means it's going from pi over 2 to 3 pi over 2. Is this good with what everybody has right now on their paper? You guys have this, okay, because you just did the graph. All right. So what we're going to do next. Somebody tell me the transformations that are going to take place by multiplying this function by -2. Julia. Uh-huh. Good. So there is a vertical reflection here as well as a stretch by 2. Okay? Now, when we stretch, remember, we're kind of stretching from this middle axis, meaning the points that are on that axis at 0, those are not moving by a stretch or compression vertically. It's that these maximum and minimum points are getting stretched or compressed towards or away from those middle points along your function. Okay? So right now, this maximum is 1 unit above those middle points. Where is it going to end up? Right now, it's 1 unit above them. Where does it need to be? 2 units above them because the amplitude now needs to be 2. Okay? And then same with the minimum. I'm not going to draw it in yet, though, because there's two transformations taking place here in this negative 2. Me changing these 2 points here takes care of the change in the amplitude of 2. But what did we say the negative is going to do? Flip it vertically, which means what I see as a maximum is now going to become a minimum, and what I see as a minimum is now going to become a maximum. But again, a vertical reflection, these points are going to remain untouched because they're along the axis. Okay? Matt?
Could you just change the 1 on the y-axis to a 2?
Yes. Did you guys hear what Matt said? Going along with our idea of changing scale. He said, could you just change the 1 on the y-axis to a 2? Totally. You can do that and just flip it over and you'd be done. We're going to go through 1 completely and slowly so everyone sees. And then you guys are going to be like, oh, I know the middle points are going to end up here because of the +1. And you guys are just going to like put your curve where it goes as you get more and more familiar. But if you had to walk through all the transformations, this is what it looks like. Okay? Is everybody comfortable with what this new curve looks like? Okay? We changed the curve that had all the horizontal changes by putting in this vertical reflection and a stretch, which changed the amplitude to 2. Is everybody okay with this? Any objections to me changing the screen? All right. So what's the last thing we have to do? What's the only thing we haven't done from our original function? +1. What's the +1 going to do? Move everything up 1. So basically, this kind of middle line that I identified here with the dashed green line, it's going to really be where now? Up 1, and it's going to be here. What's the maximum height your function's going to reach once we move it up 1? 3. And the minimum height? -1. Okay? So we'll go one more over. Oops, maybe not. Don't know what I did. All right, so what you guys had. And like Matt said, you could just change the scale instead. So this is what you guys had. And we talked about moving it up 1 basically makes all the center points line up here. Now again, this dashed line is not really part of the graph. If you guys want to put that lightly on your graph to determine where those like median, middle points are going to be running across your graph, that's fine. So all these are moving up 1. So this point's going to be here. All the points that were at 0 will be up there. Okay. And then like we said, the maximum, instead of just being at 2, needs to be 2 units above these middle points, so it will be up here at 3. And the minimum needs to be 2 units below these middle points, so it will now be down here at -1. This would be your graph. Now, if you wanted to complete that graph, you would now continue this pattern of points. Okay? So I'm back at the 0. I would now go down to the minimum, then back to 0. On this side of the graph, from here, I would go to the maximum. I'd go back to 0. If there were marks on this other side, I'd go down to the minimum. So I can then draw my graph over the entire span of area that I need to draw my graph. Is this okay with everybody? So the transformation should be review of what you did before. Okay? The only thing that's different is instead of just horizontally stretching and compressing by moving numbers of spaces, we're rescaling our graphs. And you might say, I don't like that. I'm not going to do it that way. Again, I'm only worried you're going to run into trouble when you have to do things by thirds or sixths or something like that. Okay? And then you should know for this graph, the period as well as the amplitude. You could have gotten that from the original equation. We calculated the period right at the beginning. Because of this 2 in here, we just took our 2 pi, our normal period, and multiplied it by that horizontal compression, which gave us the period of pi, which is why that 4th mark on our graph was pi. Okay? And the amplitude of the graph, we could recognize right at the beginning as well because of the a value of 2. Okay? The amplitude is not positive or negative because, remember, it just tells you how far the waves go, so you would always list the amplitude as a positive number. Okay? All right, is everybody okay with graphing this? Yes? No? Questions before we try one? Like where you try more of it on your own? No? All right. On the screen. Hold on. All right, so your job. 2 sine pi 6 theta plus 1. Now, theta is like what? X. It's the angle, okay? One comment about this. I'm going to help you guys just set up the period part of it. The pi over 6 here, is that a shift? No. So James is shaking his head no. What is that going to affect? The period. Okay, which is kind of weird that it has pi in it. So I wanted to specifically use this example because sometimes you see sine or cosine functions and the x-axis is just numbered with like 1, 2, 3 radians. And you're like, how is it not pi over 2 or something that represents an angle we're used to seeing? Something like this affects that. So let's do this the normal. I'll set up the scale with you guys. What did we say to do first when you see that b value, something that's going to affect the period? What should we do? We're going to change the scale. Okay. How do we determine what the new period of the graph is? Good. 2 pi divided by that b value or times the reciprocal of that b value, right? Just like a horizontal stretch or compression. You took the normal distance and you multiplied it by the reciprocal of this. So this is pi over 6. We're going to multiply by 6 over pi. Those pi's will cancel, giving us a period of 12. Random, right? 12. So that just means, and you guys can extend the graph here, but that just means I'm going to make the fourth mark on my graph 12 if I'm looking at a period from 0 to there, which means what is this first mark on my graph? 3, because it's just a quarter of 12. So this goes 3, 6, 9, 12. On the other side, it would be negative 3, negative 6, negative 9, negative 12. Okay? And you don't have to do this transformation already. It's done. Okay? And you would have your little sine function floating through here if these are ones. Okay? So what I've just graphed is the sine of pi over 6 theta. What hasn't been incorporated to the graph yet is this 2 and this 1. So go ahead and finish the graph incorporating this amplitude of 2 and the vertical shift of 1. Okay? And then we'll look at what they look like. All right, check and see. So I have a period of 12, an amplitude of 2, and this is what my graph looks like. And then again, if I wanted to fill that in on the rest of the graph, I would continue this pattern, right? Sorry, this is supposed to be at negative 1 if it looks like it's at negative 2. Up here it doesn't, but over there it does. Okay. Oh, sorry. Okay. So this way, you move one period, but like in your homework, a lot of times it'll say graph it from 0 to 2 pi. I wouldn't originally graph it from 0 to 2 pi. I'd move it all, and then I'd continue that part if it wasn't already in my graph. Okay. All right, so the period's 2 pi. The amplitude is 2. What is the domain of this graph? All real numbers. And the range? Good. So greater than or equal to negative 1 and less than or equal to positive 3. So learn the parent functions and then use the transformations like you always have to get through the graphs. The only thing that's slightly different is the period of the function. Remember that theta is just like x. So here's your next challenge. Can you graph negative 1/2 cosine of 3 times theta plus pi over 6? Okay. Questions on your graph. So things you should be able to get. The curve in the right place. So yes, your points should be in the same place as mine with the same scale. If your scale is different, you should have other marks to note the places that those points are. The period should be 2 pi over 3. The amplitude 1/2. The domain is all reals, and the range is between negative 1/2 and positive 1/2. Okay? All right, try one more before you go. just to make sure we all have the right scale to begin with, since we're new at this. This is a horizontal reflection. You're going to have to take care of that next. But again, my starting place, a couple people have said they don't know how to start. I look here and I see the word cosine, and I start with what the 5 main points on that first period of the cosine graph look like. And that's between 1 and -1, and that's a period of 2 pi. But I'm going to adjust that 2 pi measurement based on this. What is the b value in this problem? It's negative, which means horizontal reflection. I'll deal with that later. But what's the number that's going to affect the period here? 1/3, right? This fact that theta has been put over 3 means 1/3 is that number that's in there for horizontal stretch or compression, which means to find the period, I take the normal period and I multiply it by, just like you did before with your horizontal stretches and compressions, you multiply by the reciprocal of whatever's there, giving us a period of 6 pi. Okay? So I'm going to change this to 6, which makes this like 1.5, 3, 4.5. Okay. Okay. All right, you guys finish on your paper. I'm going to finish putting in the changes up here so you can check the answer. All right.